Hello, everyone. Thanks for attending our webinar. I am Eric Blankenhorn. I'm an engineer here at wolfSSL, and I will be discussing the basics of the MQTT protocol and how the wolfMQTT client can help secure your IoT network. We'll start with a discussion about the specific needs of the Internet of Things. That'll lead us to an overview of the MQTT protocol itself. Next, we will review the different specifications that are supported by the wolfMQTT client library. Then we'll take a look at the architecture of the library, including a quick look at the configuration options and the build process. That leads us to talk about the many rich client examples available alongside the core library. Next, we can look at some of the ideas we have for the roadmap of wolfMQTT. And lastly, we'll answer any questions that you might have about the protocol or wolfMQTT specifically. The primary concern of many IoT projects is one of resource constraints. These devices may have tight power budgets or small memory availability, or they might be operating on networks that are either unreliable or expensive, each of which requires minimizing the amount of data transferred. The MQTT specification is free to use, which has greatly enhanced its popularity among developers of devices that number in the tens of billions. Since the protocol is easily scalable, industries across the spectrum have found it to be suitable to their application. Also key for developers is how friendly the API is. There are really only 8 primary functions in the wolfMQTT library needed to have a fully functioning client. So MQTT stands for Message Queuing Telemetry Transport, or MQ Telemetry Transport, depending on who you ask. It was designed specially for lightweight embedded type systems, but it's scalable to allow for efficient large networks as well. Individual MQTT packets are very small, and publishing a short message, including overhead, is in the tens of bytes. The publish and subscribe methodology allows publishers to send lots of small bits of data that are related to a topic. Then that data will be sent to the subscribers of the topic. This allows loosely coupled systems in which devices do not need to have a state knowledge of their peers to communicate with them. Through the use of repeaters and bridge devices, the peers don't even need to exist on the same network topology. Even more important to devices that may be powered off to conserve resources, messages can be stored and resent until the transmission is successful. Brokers are the central point of contact for all of the MQTT clients. Brokers act as the directory of all connected clients, the index of all the topics, and the distributor of all the messages. So, choose your broker wisely. The protocol specifically recommends using TLS to secure MQTT traffic. Devices that need to go offline to conserve power can use session resumption to quickly reestablish the connection. This level of protection adds overhead, but luckily we have the world's best TLS library available, wolfSSL. So quality of service is useful for defining a message's integrity. Things like network capacity, tolerance for missing data, and tolerance for duplicate data are all considerations when choosing the quality of service level. When a client subscribes to a topic, a quality of service level is specified. Likewise, when a client publishes to a topic, a QoS level is specified. The highest QoS level is determined by the party with the lowest quality of service. In other words, client A can publish at QoS 1, but if the subscriber, client B, used QoS 0, then client B will only be sent a message of the QoS 0 version from the broker. So with QoS 0, the broker does not acknowledge receipt of the message, and the message is not stored or retransmitted by the sender. QoS 0 is best suited for a stable network or non-critical data. Imagine something like a rain gauge sensor that reports data every minute. So a couple of minutes of readings lost here or there is probably okay. With quality of service 1, the sender stores the message until it gets a pub/ac acknowledgement packet from the receiver. In this case, a message could be sent or delivered multiple times. This is suitable when data is critical, in other words, it must be delivered, but it's okay if duplicate data is received. Also, network restrictions like bandwidth or cost don't allow for the full QoS 2 handshake. Imagine a blood pressure monitoring application that is sent reports from a sensor containing a timestamp and the blood pressure reading of an astronaut. The application can ignore readings with the same timestamp, but all of the readings have to be recorded. This would be a good candidate for QoS 1. So with quality of service 2, it's the most thorough, but it's also the most costly. It takes 4 transactions for each published message to complete a delivery. QoS 2 should be used when the application cannot handle multiple messages. So take, for example, a firmware delivery that would waste precious network bandwidth receiving a duplicate message, or perhaps require all of the device's storage capacity to even receive the payload. So the MQTT specification allows up to 256 megabytes of payload per message. However, the actual payload maximum is often limited by the broker. For example, the limit for AWS is 128 kilobytes, while Azure limits client to broker transfers to 256 kilobytes, and broker to client transfers are limited to only 64 kilobytes. So again, choose your broker wisely. The last will and testament allows other clients to be informed when devices have lost their connection to the broker. During a normal session, a client would disconnect, indicating an intentional, orderly shutdown. But if a broker loses the connection ungracefully, then the disconnected client can inform its peers using the last will and testament messages. Also, as you can see, there are only 14 packet types for the 3.11 protocol. Packet sniffers like Wireshark are aware of MQTT traffic by the packet header. It can be very useful for a client application to send a single subscribe packet on initialization and be notified of messages for multiple topics. The term publish here refers only to the message type. A message that is published by a client will be sent to the broker. The broker will then publish that message to all the clients who are subscribed to the message's topic. Messages can also be marked for retention to be stored on the broker. If the message is retained by the broker, then new clients will be sent that message when they first subscribe. This can be useful for conveying information like system state. So version 3.1.1 is the successor to version 3.0. and it's the only protocol version currently supported by AWS and Azure. Most implementations of brokers today are using 3.11. Version 5 was completed in March of 2019. It adds support for properties to be sent along with the command packets. Properties are a simple way to add custom metadata to the in form of key value pairs. These can be used, for instance, to describe the format of the payload data. Recovery from command failures can be complex, and new error messages from the broker can be used to help the client know what went wrong during a failed publish or subscribe. Topic aliases allow integer representations of complex topic names. This can significantly reduce the bandwidth required for commonly sent messages. The sensor network protocol was developed around 2009 to help enable battery-powered devices on low bandwidth wireless networks to benefit from MQTT. The SN protocol allows a gateway device to communicate the full MQTT messages to a broker over a normal TCP-capable network. Message packets from an MQTT SN client are even smaller than MQTT through the use of topic IDs, a 2-byte value that is used to represent a topic name. So here's where we would like to ask a little bit of support from our listening audience. Whenever we're done with the presentation, there'll be a survey, and we'd like to ask some information from you. So we're curious, if you're using MQTT, could you tell us what protocol your application is using? And here are some of the options we have here. And if you don't, or if you're not using MQTT right now, which one do you think would work best for your application? So now I'd like to talk about our architecture a little bit. The wolfMQTT library is organized into 3 distinct components: the client, the packet, and the socket. The client contains the actual API functions listed here: connect, disconnect, publish, subscribe, unsubscribe, ping, and wait message. The packet component is where you can find all the internal functions for building and parsing the packet structures. And lastly, the socket component is the interface for the lower level networking layer. This could be straight through to TCP, or it can be enabled to use TLS, courtesy of wolfSSL, of course. As you can see, it's very easy to configure the library for the various protocols and features that are supported. If you disable the TLS support, then the wolfMQTT library can actually be compiled and run completely independent of wolfSSL. But why would you want to give up the world-class TLS connection? Debug messages are crucial for figuring out why your application is not quite working right. The last one there, multi-thread, allows independent tasks to use the library without any internal conflicts. This adds some overhead, so we made it configurable so as not to bloat the library size for size-conscious applications. So moving on a little bit to building. So building the library is very straightforward. You'll have to watch another webinar for the instructions if you want to install wolfSSL. Just kidding, it's in the README. After cloning from GitHub, you simply autogen, then configure, and make. And that's it. So now this is one of my favorite parts. Let's talk about the examples. The examples are crucial, but often overlooked part of any successful library. We have taken the time to share as much as possible. The standard MQTT client example is quite powerful. You can specify a host, port, quality of service, topic name, etc. Pretty much everything you need to test a broker connection. It's also where the MQTT version 5 specific parts live. The non-blocking client is very popular with the microcontroller crowd. The multi-thread example uses a publish task, a subscribe task, and a message wait task, and a ping task to demonstrate that feature of the library. The firmware example is pretty nifty. It has two parts. The first is the firmware push, and it uses wolfSSL to build a hashed and signed firmware image, and then it publishes it to the broker. The second part is the firmware client, and it's subscribed to the topic, and it's waiting for the firmware to be published. Whenever the broker sends the message and the firmware client receives it, then the firmware image is unpacked and verified. So this is basically what you would actually do for an embedded device. The other examples use a couple of shared utility files. The MQTT simple demo is completely self-contained, and it's very straightforward. The sensor network client requires another component besides just the broker, the gateway. The gateway handles communication over UDP on the sensor network side and retransmits the messages to and from a broker on the TCP side. So now we're going to talk about the big three. Based on support questions, these brokers probably account for about 75% of the MQTT client library usage. That's to say roughly 3 out of 4 users of wolfMQTT are connecting to one of these brokers. Now, I should mention that we do get a lot of questions about Google Cloud Platform also. And so that's one of the things that we definitely have planned. And I should probably replace one of these with Google Cloud. So those are our examples. They're all neatly contained in the examples folder. There you can also find a couple of utility files that contain code that is used by the examples, but not necessarily needed in the wolfMQTT library proper. The sample client is roughly 9 kilobytes. You can see in the output that the client is connecting to the mqtt.eclipse.org public broker. This is the default. You can also see that TLS is being used to secure the connection. You can see the connect, subscribe, publish, and oh, there it is. Yes, this confirms it. This webinar is awesome. So here's our last poll question. If you wouldn't mind letting us know, we'd like to know what your application is using for the broker side of the connection. So if you would also tell us, besides what protocol, if you could also tell us what broker you're using. And we've got a few listed up there. If you're using something else, just let us know. So this is kind of where we're looking to go in the future. This list consists of things that some folks have asked if we have, and some things that we just think would be neat to have. We currently support TCP and TLS, but WebSocket support is always gaining momentum. We can always use more examples. One that we have planned right now is Google Cloud Platform demo. GCP uses JSON web tokens for authentication, which is actually very simple with wolfSSL. A full command line interface that would allow scripting applications to run could be pretty neat. Right. Also, currently the MQTT sensor network library is not secure. The nature of sensor networks often means that it's not feasible to add overhead or to use more power, but we are the kind of people that think all data should be encrypted. And as always, we're interested to hear what else we should support, so please keep your suggestions coming. And I think that's all. So if there are any questions, feel free to ask them now or send them in later.